Our speaker today is Jun Ye. Jun, thanks very much for being with us. It's a great pleasure of having you as our speaker today. He is a fellow at NIST in Boulder, Colorado, and also a fellow and professor at JILA, which is a joint institute between the University of Colorado and NIST. He has received numerous prizes for his work, among them most recently the Norman Ramsey Prize, the Rabi Award, IEEE, the Rabi Prize. He is a Gordon and Betty Moore Distinguished Scholar. He has received the EFTF Award and the Gold Medal from the Department of Commerce. And there are many more than I could read right now. He holds a number of lectureships and guest professorships. And we are really looking forward to your exciting talk today, Jun. And the title is Clock, Quantum Matter, and Precision Physics.
Well, thank you, Christian. And thank you, Klaus and Stefan, for inviting me to come here and share some of the results. Even though it's through the virtual medium, it's great to talk about physics and seeing some familiar faces of colleagues that we haven't seen each other for more than half a year, and I really do miss that aspect. But so in the next 15 minutes or so, let me share some of the recent work as well as some of the vision that we're moving forward on building clocks and how that relates to precision physics, which is the theme of this particular seminar series, and how that draws connection to quantum science frontier that is very active right now. And that's why in the title have the quantum matter, that I firmly believe the next generation of clocks and precision measurements will have a very strong benefit to draw from quantum science, where the quantum material will start to be used as a real resource to advance the measurement frontier. So with that said, let me just give you a quick slide about the progress of the last 6 decades or so on atomic clocks, and that the atomic clock is becoming increasingly more sensitive sensors of space-time. As you can see, from 1950s all the way to 2020, over the last 70 years or so, the clock performance has come down by essentially the same order of decades, like by 7 decades over the last 7 decades of time. And the reason being, actually, always sort of creative, revolutionary new technologies have come along the way. And for the example of the latest clock, that's in the generation of so-called optical atomic clock, where the clock frequency is operated at the visible or mid-IR, or even in the future, VUV, vacuum ultraviolet spectral regions, and use technology like frequency comb to translate that optical frequency or phase into the microwave domain so you can count as a time. You can see this progress of the slope is extremely steep, and it's still ongoing. And we can give credit to a number of quantum technologies that's been developed by our colleagues and pioneers and so on. For example, since 1970s and 80s, people have been advocating very high quality factor optical transitions in both trapped ions and neutral atoms. We are now taking advantage of them. We have been developing new laser stabilization methods where optical coherence can last for tens of seconds now. We can use many atoms in optical lattices to engineer quantum antibody states that would be beneficial for precision physics. As I mentioned also, the invention of optical frequency comb connects the optical domain of frequency phase information to the microwave domain. And at the current state of the art, the accuracies has reached a fraction of 10 to minus 18. That's equivalent of gravitational redshift, about a centimeter on the surface of the Earth. The precision of the clock measurements have reached a small fraction of 10 to minus 19, 10 to the 19 level. And the goal is to really continue to advance this to the level of 10 to minus 20, 10 to minus 21, where there is truly a new frontier of using clock to probe fundamental physics lying ahead. And so my lecture today is really about giving you some of that preparation work we are doing to see how we can advance towards that level of measurement accuracy and measurement precision for clocks. So the connection to quantum science, I think, is very obvious for everyone. And as you prepare a quantum system for long coherence time, you want to be able to protect that quantum coherence. You want to use as many quantum particles as possible to either move forward on the standard quantum limit, which is proportional to the number of particles you have, or even enjoy starting to take advantage of entangled states and so on to further push measurement frontiers beyond the standard quantum limit, such as actually LIGO is already moving forward with the squeezed light. And by engineering many body states together, you will not only be able to engineering quantum states that's robust against perturbations, but it provides enhancement of measurement precision. So for clock business, the efficient state preparation, protecting of quantum coherence, and finding robust optimum measurement is what we have been relying on the past few decades for moving precision physics forward, including clocks. At the same time, as I mentioned, quantum entanglement, quantum system engineering, and really thinking ahead using such quantum machine for useful applications, solving some practical problems in the society. That's really the new front of a quantum science, and you can actually obviously see these two fields, precision physics, quantum science, go hand in hand, helping each other. And let me just take an example of us talking about clock stability for a moment. You know, here is a diagram showing a comparison between a one-dimensional optical lattice clock versus a three-dimensional optical lattice clock at JILA. And currently, it's showing a stability of a field path 3 times 10 to the minus 17 at 1 second. And if you average it for an hour, it reaches stability of 6 times 10 to the minus 19 in 1 hour. This is far faster than any previous clocks by a factor of 10 or more. But I would argue that that level of performance is still far from what's being promised to us with these quantum systems that we have. And that's really the point that I'm going to belabor throughout my lecture today. But even at this level of measurement precision, if you think about connecting time and space through Einstein's general relativity, we know that 1 centimeter is 10 to the minus 18. So if you can reach below 10 to the minus 18 in 1 hour, in the middle of 10 to the minus 19 in 1 hour, that means you can measure gravitational potential differences of 1 centimeter in just about 20 minutes. And we think in the coming years, this number will be pushed by another factor of 10, maybe by another factor of 100 and further. And that means that you will have a real-time space-time probe being able to be very sensitive to gravitational potential change, local position invariance, testing relativistic geodesy, and so on. If one can do quantum engineering, bring these devices as a portable systems out of the laboratory, and such effort is going on right now at PTB, in RICON, and NIST, and so on. So let me just tell you where I think the advances is going to come from both the one-dimensional optical lattice and the three-dimensional optical lattice clocks. In the 1D system, essentially it's a one-dimensional, so-called one-dimensional optical lattice system. It's just a single beam being retroreflected, or building use a cavity to build up the standing wave field. And so you create an array of a stack of pancakes. That's a two-dimensional optical traps. And on each optical trap, in each pancake, you trap about a dozen or so, a couple of dozens of atoms there. As you do clock interrogation, you're rotating that spin, the fictitious spin in the optical domain. And that's where you bring the block vector from pointing to the south pole to the equatorial plane, and eventually letting it go through Ramsey fringe or Ramsey cycle or Rabi cycles to probe the coherence between atom and the light. And of course, these atoms we actually use fermions, and they are quantized in the direction of this tightly confined direction along the vertical axis here shown on the screen. And they occupy actually basically zero band, the motional band, as we say. But in the transverse direction, they are thermal atoms in these experiments, and they occupy a number of motional states. And when you anti-symmetrize the wave function between two fermions, you can have the anti-symmetry being taken by the motional degrees of freedom, as is shown in this expression, N1, N2 minus N2, N1, while the spin degrees of freedom can be symmetrized. And in that case, the atoms are actually interacting through the so-called P-wave interactions. And that gave rise to actually somewhat collective spin interactions that can be described by this particular Hamiltonian, the SZ square term, the so-called single axis twisting spin Hamiltonian. And it gives rise to this collective interactions that can actually provide correlations between individual quantum fluctuations of individual spins. So while this is an interesting system to study spin Hamiltonians and spin squeezing and so on, those interactions that does limit how many atoms you can use per pancake. In fact, ideally, for the most accurate clocks, you would want to use only one atom per pancake, because if you have two, there are potentially interactions there. And also this interaction gives rise to finite coherence time. And so what we are planning to push forward in this one-dimensional optical lattice system is to actually put it inside an optical cavity with a finesse of 20,000 or so, just for talking, and use collective physics enhanced by the cavity QED to do spin squeezing and to really push forward on the clock performance there. And it's actually interesting if you look at it, spin squeezing, it is particularly in the regime where the coherence time is shorter than what's being afforded by the intrinsic spontaneous lifetime of this atomic system, where the quantum speed up by spin squeezing or correlated entangled quantum states of spins would be particularly useful. In some sense, you can think of as, because of limited coherence time, I'm using quantum correlations to speed up, to give my measurement a better bandwidth. And here you can see that this particular chart that was calculated by Michel Lukin's group back 5 years or so ago, showing that if you can have GHZ entanglement or spin squeezing and so on, as you go to larger particle numbers, you obviously gain at shorter average times. But once you go beyond the coherence time given to us by either the local oscillator of the laser or by interactions of these many atoms, that's giving rise to a limited coherence time in the system, then once you go beyond that coherence system, the spin squeezing advantage of entanglement and so on start to diminish. It's still better than the classical measurements, but in terms of the gain, starts to get smaller and smaller with the best classical interrogation schemes you can come up with. So there are other technologies as we push forward. For example, one is by advancing the local oscillator, the optical local oscillator, to better coherence time, eventually to match all the way to the individual atoms' spontaneous limited coherence time. And suppose we can protect the quantum system of tens of thousands of atoms, all reaching the coherence time that's limited only by the spontaneous emission lifetime, then in principle, you don't need to do entanglement at that kind of a coherence limit. And that's really the other avenue that we are pursuing, which is in a three-dimensional optical lattice. Here, the goal is clearly to preserve atomic coherence to be as long as we possibly can, limited only by, again, spontaneous emission lifetime. And in strontium's case, on between the two clock states, this coherence can be as long as 160 seconds, nearly 3 minutes of a quantum coherence. And if you can pack 1 million atoms into the three-dimensional optical lattice, then you can dream about making a clock that's at a fraction of 10 to minus 20 at a 1 second averaging time. And that's really 3 orders of magnitude better than the current best clocks that can demonstrate today. So there you can see the room for improvement is a fairly spacious there. systems like this, on the other hand, while I'm emphasizing trying to avoid interactions, in fact, it provides a very interesting system to study some of the canonical, outstanding condensed matter models, such as the Fermi-Hubbard model with spin orbital coupling, with collective dipoles. So there's a lot of interesting physics all in the system. And if you do not understand it, of course, that will limit the coherence time, that will limit the measurement accuracy, and will limit how you can take that quantum resources to enhance the measurement precision. So in some sense, you can see the quantum sensing and the quantum simulations by understanding these Hamiltonians interacting many-body systems are very much the two sides of the same coin. They are strongly connected. In order to advance one area, you have to really work on the other. And that's why it's connected to this very interesting new front of quantum simulations, whether it's programmable or just analog quantum simulations. These systems also provide great opportunities. So let me talk a little bit about the atomic system that we put into these three-dimensional optical lattice. We work with the strontium atoms it's a fermionic isotope strontium-87 with a nuclear spin of 9.5. So you can have 10 different nuclear spin states, that is as shown here. And the two clock states are both in the J=0 electronic states, single S0 or triple P0. So the hyperfine interactions in each electronic state, because of I.J=0, there's no J, the hyperfine coupling is small, is 0, sorry. So we are talking about fermions with decoupled spins. One is a nuclear spin, the other one is a fictitious electronic spin. And because of I.J=0, it means that when they bring these atoms together, even if they have different nuclear spin states, they always interact electronically in the same way, which means that you can use one scattering length to describe all the nuclear spin states. And what's really interesting about this is that recently we were able to demonstrate using techniques like that, so-called ACOing symmetry, which is N represents the number of nuclear spins you have. Because they are all symmetrical in terms of how they interact, you can simultaneously produce 10 different Fermi Cs. Each Fermi C represents a particular nuclear spin state. And you can have 10 Fermi Cs all working together very efficiently to produce the degenerate Fermi gas in just under a second after laser cooling to produce 40,000 atoms per nuclear spin state. And each Fermi C would have T over TF. TF represents the Fermi temperature of 0.07. So very deeply degenerate Fermi Cs, and 10 of them all at once in this extremely fast time scale for evaporation. And that's actually quite kind of interesting. We are all familiar with boson BEC. You know, we all know as you cool the temperature down of a particular system, if the particles are bosons, they collapse to the ground state and form the so-called boson-Einstein condensate. While the fermions, they form the so-called degenerate Fermi gas, where the energy levels are very uniquely occupied by one quantum particle per state, and as obeying the Pauli exclusion principle, anti-symmetrization of the wave functions. But if you put the so-called SUN symmetry system together, what you have, in fact, is 10 Fermi Cs living together that it gives rise to hybrid Bose-Fermi characters. And on one hand, these are 10 different Fermi Cs, each pristine, low entropy. But when you put 10 Fermi Cs together, because they can interact, you start to give rise to these bosonic interacting quantum systems. And you can tune that interaction by just controlling how many spin states you put it in there. And this is where you can build novel quantum states, such as spin liquids. For example, even at 0 temperature, when the entropy is removed from your external degrees of freedom, you can see because of there's a spin, depending on how many spin states you occupy, you can have entropies that's living in those spin states. So one interesting area is looking at the Fermi C. You always look at, for example, the Pauli exclusion principle. One area is looking at the density fluctuation of a gas. In classical gas, density fluctuation equals to the number of particles, the variance of the fluctuation. While in the Fermi gas, the variance is greatly suppressed. As we know in the center of the Fermi gas, the particles are very orderly displaced from each other. And so the fluctuation scales with a T over TF for Fermi gas. As you go to lower T over TF, better degeneracy, the fluctuation becomes frozen, becomes small. And this is what people call incompressible Fermi gas. And what a typical measurement would be like taking a column density and they remove the Fermi Dirac distribution and look at the variance of the density fluctuations. And that can give rise to the characterization of how much density fluctuations being suppressed as you get into the Fermi degeneracy. And that shows, you know, in the open diamonds, that's the thermal gas where the variance on the vertical axis scales with atom number. But if you get to the quantum regime, the so-called degenerate Fermi gas, the variance is far suppressed from the thermal gas situation, as is shown by the red circles here. Because of the interaction, the SUN symmetry interactions, it further reduces the compressibility of the Fermi gas. So really make the system with the tunable interactions display very characteristic sort of both the boson and the fermion natures of the system. Well, boson is only because of the interaction is giving rise correlations between different spin states of the nuclear degrees of freedom. So with that, if we want to select particular Fermi C, we also have techniques where you can use optical stock tensor shift, shining laser beams tuned to an appropriate frequency, and it basically gives rise to different tensor vector or scalar frequency shift to these different nuclear spin states. In this particular experiment, we use stock tensor shift. And you can pick, for example, only the spin 9½ state to be trapped. And by doing that, you can remove all other spins without giving any heat to the system and just leave a particular Fermi C for yourself. And you can use this to load into the optical 3-dimensional lattice. And that's what this is. You can have a single spin state loaded into the optical lattice in 3 dimensions. And when you look at spectroscopy features, you can see that these atoms are loaded because they are at such a low temperature, loaded into the lowest possible motional band of these 3-dimensional optical lattice in all 3 directions, X, Y, Z. Therefore, as you excite the atom, you can see a very strong carrier in the middle. And then you can see 3 side bands on the blue side, on the positive frequency side, because you can drive the transition to gain a +1 motional degrees of freedom of quanta in X, Y, or Z directions. Those that have 3 different motional frequencies among 3 different spatial directions. But on the red side of the spectrum, you don't see any excitation. That's because these atoms have already been cooled to the quantum mechanical ground state in all 3 directions. If, however, you say, well, let me open up the 10 Fermi Cs that I just talked about, and in that case, of course, Pauli exclusion principle will not forbid that different nuclear spin states to occupy the same ground motional state. In that case, what you see actually the spectra changes. You have the carrier as before, and then what you see is that you will see 2 side bands. These side bands are actually quantized interactions due to the fact that the anti-symmetrization of 2 fermions at the same lattice site will have to be anti-symmetrized, and that anti-symmetrization can come from either nuclear degrees of freedom here, the so-called EG plus, or it can come from the electronic degrees of freedom here, the EG minus. And because of that, it gives rise to 2 interaction peaks on either side of the carrier. You can, of course, occupy more than just having 2 atoms per site. You can have 3 atoms, 4 atoms, 5 atoms per site. And what it really is noticeable feature is that regardless how many particles you put it in a particular site, you always have 2 interaction side bands associated with one particular configuration. And that's because of the SUN symmetry, that because all these different nuclear spin states interact electronically exactly with the same strength, therefore you can only have anti-symmetrization in the nuclear degrees of freedom or in the electronic degrees of freedom, and gives rise to 2 different interaction side bands, and but that's it. Everything else is degenerate. These actually interaction side bands, as you drive them, you can actually image them and you can select them, they gives rise to strongly entangled states, either in the n-body W state or highly entangled between orbital and nuclear strings for when you have more than 3 particles occupying the same lattice site. And all of that can be spectroscopically selected, imaged, and it really sort of see the shell structure of how these various different sites being occupied by the numbers of number of atoms with different nuclear spin states in there. So of course we can zoom into a particular nuclear spin state, n equals to 1. That's 1 atom per site. And there we can actually start to do clock spectroscopy. For example, here you can combine microscope to image along with very high spectral resolution of the laser to select, to understand the different regions of atoms in the 3D lattice, how they respond to different external perturbations. For example, this perturbation could be coming from the optical lattice field that we pick the so-called magical wavelengths where the excited clock state and the ground clock state should have exactly the same AC stock shift by the trapping light. Therefore, the trapping light is not giving rise to a frequency shift in your clock transition. But you can, of course, purposely move that away. For example, in this particular case, I moved away by 1 Hertz between the ground excited state in the AC stock shift. And you can actually take an image of it, almost remind you of like a Newton ring when you look at a convex lens pieces, and you can see different optical interference fringes due to the thickness change as a multiple integer multiples of optical wavelengths. Here's just like as you go away from the center, the frequency shift goes through multiples of a clock modulations. So you can see those fringes, all the atoms in the ground state, all the atoms in the excited state, all the atoms going to the ground state again, and so on, depending on your Ramsey or Rabi spectroscopy that you are doing across the regions of the spatial 3-dimensional optical lattice. Excuse me. You can also apply a magnetic field gradient that causes frequency shift across a plane of optical lattice trapping potentials. And again, if you do Ramsey spectroscopy, you can see stripes, ground state, excited state, ground state, excited state, again, indicating as you move the different Ramsey time, you can select the frequency that's in resonance with your particular spatial region where the frequency is being shifted by the gradient magnetic field. So all of that can be useful to characterize the system itself. You can see the 3-dimensional optical lattice itself becomes a sensor to sensing some sort of field gradient of a force. And I'm going to come back to this point later. If the sensitivity of the clock is so good, you will be able to measure directly the gradient of the gravitational potential in the 3D lattice. So now let's talk about what kind of a coherence that we can achieve now. Here shows that as we go to very large trapping depth, the coherence time goes down to a few seconds. And as you go to very shallow optical lattice, on the other hand, the coherence also comes down. And so far we have 12-second atomic coherence. While it's a great, at the time for the lattice experiment, this really is a record coherence time. Nevertheless, it's far away. It's a factor of 10 away from what being promised to us by the strontium atom itself. So what is limiting us? Well, on the high intensity side, when the lattice is really deep, the coherence time is limited due to the fact that the excited clock state, the triple P0 in the bottom left figure, can scatter the 813 nanometer lattice light through this Raman process where the photon can be scattered to a virtual state near triple S1 and it decays back to triple P1 or triple P2, and the atom then gets pumped through spontaneous decay into the ground state of single S0. And then we can actually see that effect. We can see by putting atoms in coherent superposition between single S0 and triple P0, and you wait there for a few seconds, you can see the population in the triple P0 start to go down while the population in the single S0 start to go up. So this Raman process is very visible in the 3D lattice. That's what's limiting the coherence time. So then you say, okay, well, then you should just use very shallow lattice, but we also see the coherence time is going down. The reason being actually there's a tunneling, and that's not surprising to anyone. if the lattice is too shallow, you can have the atoms tunnel back and forth if the lattice has holes in the system. And here actually shows in the bottom right corner, I'm showing a fringe that's taken at the center of the 3D lattice versus on the edge of the 3D lattice. You can actually see the 3D lattice on the edge. The coherence is much longer than in the center. And it turns out, if you think about a system which is not fully filled, if there are filling defects, if the atoms is in the middle of the trapping center, the external potential curvature is near zero. And so the lattice sites are more degenerate with each other, their energy levels, so that facilitating the tunneling of the atoms back and forth. While if the atoms are trapped near the edge of the three-dimensional optical lattice, there's energy offset between neighboring sites. And if this energy offset delta is greater than tunneling T, you can suppress the tunneling. So this is a very simple explanation that we have tunneling induced dephasing. And there are obvious solutions. One most obvious solution, and yet technologically really innovative way of doing this, is recently being demonstrated by Adam Kaufman's group in JILA. We are in collaboration, but of course this effort is also going on in a number of different laboratories at Caltech, in Princeton, and so on. And you can actually see that the tweezer array, of course, initially came up from a number of pioneering groups, both in Europe and in the US for quantum information processing. But here you can see the advantage of using systems like this for quantum metrology. And by trapping atoms in the optical tweezers, you can completely shut off. The distance between these atoms are a few microns, so you can completely shut off the tunneling. And in this particular experiment, now that it's demonstrated coherence, atom-atom coherence, not atom-light coherence, is now exceeding 30 seconds. So it's really promising that you can build these atom arrays with coherence time that's quite long. Eventually, our goal is to get to 3 minutes or so, 2 or 3 minutes. Well, let's come back down to the lattice. Well, can we have a similar sort of advantage in pushing this kind of atomic coherence to such a long time scale? And if you look at how atoms are loaded in the optical lattice in the ground and excited state, if I load with the so-called extremely low entropy degenerate Fermi gas, as I demonstrated earlier with SUN, really efficient evaporation and so on, using optical tensor stock shift to select only a single nuclear spin state to be available, and then filled in the three-dimensional optical lattice. Then in principle, and we actually are now demonstrating a three-dimensional band insulator, meaning every single lattice site is occupied by the atom. So in that case, if the lattice gets shallower and shallower, as long as you have one atom, fermion, occupying each lattice site, these atoms cannot tunnel. They will be polyblocked. Well, the problem comes from the fact that when you probe the clock transition, you are using a wavelength which is different. You know, the clock laser wavelength is not the same as the trapping laser wavelength. Both are determined by nature. So if you just naively put these two systems together, said I have a band insulator clock and I have atoms cooled to the ground state, and they're all occupying one lattice site per atom, and it shouldn't be tunneling, should not be allowed anymore. But as soon as you drive the spin from ground to excited state in a coherent superposition, where you have a phase shift due to the fact that the wavelengths of the clock drive and the lattice site are not commensurate, then you start to develop a phase shift between neighboring sites. And therefore, the atoms of neighboring sites, as they are in coherent superposition, they all have different phase, meaning they are not distinguishable. So the Pauli exclusion principle will go away. The only thing that will preventing the tunneling would be the on-site interaction. So that becomes like, you can see where the connection to the Fermi-Hubbard model is coming from now. And so we have been studying that effect quite extensively. One trivial way to overcome that problem is to build a trap, excuse me, where you can stretch the optical lattice, this building the so-called accordion lattice, where the spacing of the lattice or the lattice constant is not given by just retro-reflected light beam, which therefore the lattice constant will always be lambda wavelengths divided by 2. But by tuning the angle of the two interfering laser beams, you can actually tune the optical lattice site, and it's making the lattice constant to be, say, exactly equal to the clock laser wavelength. In that case, as the clock atoms being driven into coherent superposition from north pole to the south pole, or vice versa, or to the equatorial plane, wherever they are, the optical phase shift is always the same. In that case, you will achieve the so-called band insulator, because regardless of how the spin evolution is being driven, they remain to be identical fermions. So that's one approach one can take. Well, of course, if you do that, you might as well just make the lattice constant to be arbitrarily tunable, or you can tune the clock k vectors with respect to the three-dimensional optical lattice, and so on. So you're giving rise to a really interesting regime of quantum simulations where you can have this tunneling, competing with on-site interactions, competing with how you drive the spins with a Rabi frequency omega. And then there's also spin orbital coupling phase shift phi, which you can tune by either tuning the wavelength of the, not the wavelength, sorry, by tuning the lattice constant with respect to the wavelengths of the optical transition, or by tilting the k vector of the clock transition with respect to a particular axis of the three-dimensional optical lattice. You can varying the phase shift that I'm writing here, e to the I. J represents the site. Pi in this particular case, I happen to show a case where the optical lattice constant is a half of the optical wavelengths of the clock transition. So you can just varying that. And that gave rise to a very rich many-body physics Fermi-Hubbard model that you can use this to generate spin squeezed state. You can use this to generate cat states and cluster states for quantum information science. So this is just a quick summary of that. By being able to investigate the long coherence times of the atom in a three-dimensional optical lattice, by preserving it, you can on one hand really reach a very high level of measurement precision for clocks, but by engineering the interactions, understanding how the Hamiltonian evolves and so on, you can generate novel quantum states that can be used to further enhance the measurement precision. So all of that remains to be a very active research area right now, sort of connecting both quantum metrology and quantum sensing, quantum simulations together in a single system. But to drive all that, I need a really a stable laser to be able to do this. And if we can do that, it will enter some really interesting regime. For example, I just talked about all the entanglement and so on in the three-dimensional lattice. If we have the right laser tools to probe, to further advance the measurement precision, like I mentioned very early, that if we can reach 10 to minus 20, 10 to minus 21 level of measurement precisions, we'll be entering a really interesting regime where you can probe quantum entanglement under curved space, under GR. This just visually showing that the 3D-dimensional optical lattice is living in a curved space, and if you can have the atoms entangled on a particular plane and to the next plane, and they all have slight different frequency shift due to the gravitational redshift effect. It will be interesting to see how the entanglement limited to individual planes gets, in some sense, scrambled by the fact that there are different frequency shift per plane, and it's very quickly you will lose that entanglement due to the fact that these, or maybe get into really deeply entangled states because of the gravity is playing a role. So as I mentioned, in order to realize that kind of a dream, we really need to advance the stable laser front further. And there has been, I think, a 14-year collaboration now between PTB and JILA in the development of the cryogenic silicon cavity. This new generation of optical stable lasers have reached the optical coherence at tens of seconds, and demonstrated here by beating two different cavities and demonstrating a very, very narrow laser line width on the order of 8 millihertz or so at a 1.5 micron, showing the stability of 4 times 10 to the 17 from a few seconds to a few thousand seconds. Even a system like this is not quite enough. The coherence time of 30 seconds is not quite enough to really probe the coherence of a few minutes of a strontium atom eventually will be able to provide. So we have very active effort going on to continue to advance the frontiers of stable lasers by making the silicon cavity better. For example, there's a system that's about to be cooled down to 4 Kelvin here, and we'll see whether we can get down to 1 times 10 to the 17 level of stability. So just by looking at the silicon cavity frequency with the strontium atoms, you can, this shows the so-called modified atom deviation. What you can think of this is basically looking at a laser that's locked onto the silicon cavity and then comparing that frequency on the atom and see whether the laser frequency of the cavity is drifting away from the atom. And it's actually quite remarkable that you can look at this over a time scale of a few thousands of seconds, and the stability of the silicon cavity as measured by the strontium atom is at the level of 4 times 10 to the 17. And so building these things together, you can actually already realize a so-called time scale. And in this case though, everything is optical. The local oscillator is optical. You're not using hydrogen lasers. The optical reference, the quantum reference is optical. So everything is optical, and that's why we called it the first all-optical time scale. And this was operated for a test run for over a month last year, showing that over the entire month or so time scale that the accumulated timing error is over 1 month is about 50 picosecond or so, much lower than the conventional time scales, which you would have about a nanosecond error of a month. So this is a very appealing, systems like that as you develop, have such a 24/7 on local oscillator that can be so stable, and you can really need it to be steered by atoms only once in a while in a day, and that can already outperform the current existing time scales. So this speaks well for the future effort of the redefinition of the SI second, and also as well as synchronization for networks and so on. But since we have cavity atoms already being compared, this can be used, on one hand, very practical use of establishing timescales. At the same time, you're realizing that cavity length is proportional to the Bohr radius, while energy of the atom is proportional usually to the inversely proportional to Bohr radius squared. By comparing these frequencies with a laser connecting the length of a crystalline material to energy of an atom, you can actually start to measure the possible drift of time, possible time-dependent variations of fundamental constants, because these length scales, Bohr radius, and so on depends on, for example, fine structure constant or electron mass and so on. So that provides opportunity to search for dark matter as example. And the dark matter, we know that from astrophysics observation, we know they exist. And in fact, nobody knows, however, the energy scale of these dark matter or the mass scale of the dark matter, that ranging from very large size as the entire galaxy to maybe a very small size like a black hole, the Schwarzschild radius. And that can give rise to like a 50 orders of magnitude variations of the dark matter mass. And because of lack of evidence so far of finding particles such as WIMPs and so on in accelerator facilities as a potential candidates for dark matter, people have been increasingly focusing their effort looking for the so-called ultralight dark matter, whether it's axion or whether it's a scalar, a dilaton type of dark matter fields. And because of the energy scale the mass scale is at a much lower end, if you look at, but on the other hand, we know the density, the mass density of the dark matter in the universe because of the distance scale observations of the star moving around the galaxies, and their speed is not slowing down as you go further away. And that gives rise to a fairly good, accurate sort of estimate of the density of the dark matter. And therefore, if you varying the dark matter's mass range, you can come to a regime where the number of dark matter particles per particular spatial mode can far exceed 1. In that case, this gives rise to like a bosonic classical fields. And that's what we are looking for, is those classical fields can give, if they are coupled to ordinary fields or ordinary matter, this can give rise to variations of fundamental constants, such as a fine structure constant and oscillatory signature that's associated with a particular dark matter mass. And this dark matter field would be oscillating at the competent frequency that gives rise to, by the mass of the dark matter speed of light squared divided by Planck's constant. So, if the dark matter is a 10 to the minus 10 eV, you will have a 30 kilohertz oscillation frequency, and so on. So this is the area where we are starting to using these state-of-the-art optical clocks, especially when atom comparison or atom cavity comparison can be made at various different frequencies. Then you can use this to constrain the potential coupling between the dark matter and the ordinary matter and the fields. People, of course, have been thinking about this for a number of years now. There are many theoretical proposals, especially connecting these various different dark matter models to some experimental observables we can make. In this particular chart, for example, by looking at various different atomic transitions, whether it's S2P or P2D or hyperfine transitions, molecular rotational transitions, vibrational transitions, and so on, you can find different dependencies on fundamental constants. And by comparing different atoms, looking at the ratio of their frequency as a function of time, you should be able to be sensitive or at least set upper bounds of the potential time-dependent variation of fundamental constants. And this is one example of a clock network experiment that went on between NIST and JILA in 2018, where we connected through both the fiber as well as through air link between the JILA building and a NIST building, where the 3 different optical clocks are operated, 2 at NIST, 1 at JILA, and we can compare them across the link using the silicon cavity, stabilize the optical light to transfer the information back and forth. And a clock comparison like this, starting to be out of the laboratory, starting to be even though the clock is still in the laboratory, but the comparison can happen over a distant network, and such effort is going on very actively in Europe of a much larger time scale, length scale, excuse me. But nevertheless, here we showed 3 different frequency ratios of these 3 different clocks. They're all consistent at the mid-10⁻⁸ level and below. And this is really 10 times improvement over the previous efforts that's been undertaken on this front. And I think in the future, this will no doubt be further improved as we improve our individual clocks, as well as the network capabilities. But come back to this comparison between atom and cavity, and because we have these different dependencies, like the silicon cavity frequency is proportional to the fine structure constant to the power of 1. For the strontium, it's proportional to alpha to the power of 2, except with the relativistic corrections, you have a slight variations of that from power of 2. And then you can also compare to hydrogen maser, where it has an entirely different dependence on alpha and electron mass, for example. So comparing those, we can actually set a pretty stringent upper bound of the so-called exclusion limit of the strength of dark matter coupling to ordinary fields, ordinary matter. And you can see the cavity atom comparison is particularly advantageous as you go to larger mass ratio, a mass range for the dark matter. This as shown by this red limit that we have derived so far from comparing silicon cavity with strontium atoms. And in fact, during that comparison which was taking place more than a year ago, we did not run the clock all the time. And so there's a lot of dark time in the middle. if we had to run the clock all the time over the entire time scale that we were running it, that you will see that the bound will be limited by the green curve here. That so you can push another factor of 5 also on the bound, and this is actually with existing silicon cavity. If we continue to improve on silicon cavity by another factor of 5, you can really start to get into many orders of magnitude, especially in the high frequency and the larger dark matter mass compared to the atom-atom comparison experiments. And also compared to microscope experiment or torsion balance experiments that's being setting the upper bound and a higher dark matter mass. So with that, I just want to mention also beyond dark matter, if we can have such devices launched into space, not only will be exceedingly useful to keep the distance measurements between satellites such that you can use this for a future gravitational wave search using LISA technology. You can also build potentially a network of clocks with a very long baseline interferometry that you can use that for both gravitational wave search and dark matter search. So this turns into the whole entire clock turns into a giant telescope for some of the space-time and unknown physics as a gigantic sort of a telescope spanning the Earth. Or you can inward looking down on the Earth and look at all the relativistic geodesy, looking at the water levels or plate changes and things like that. A high resolution microscope of the Earth's geoactivities. I'm going to end my talk to just give a speculative thing really quick. And if we look at the dark matter field and the variation of alpha, if you look at all these various different dependence of atomic transitions with a fundamental constant of a fine structure constant of alpha, they'll look at the scale of basically around 1. Well, some atoms are obviously not so advantageous, like a strontium is actually can be used as a not varying kind of a standard, and use that to compare to constrain other standards such as ytterbium ion that's operating at PTV. But nothing really stands out. Maybe you go to highly charged ion, you can start to get into a fairly sensitive enhancement factor that's on the order of 100. On the other hand, if you open this up to nuclear transitions, there are calculations that's shown that for the nuclear transitions, the enhancement factor could be on the order of 10 to 10,000 or larger. So there's a fairly good scientific motivation if you want to open up a nuclear transitions for this type of fundamental physics research. And we know there's only one nuclear transition, thorium-229 isomers that could have a transition which is in the Goldilocks regime where the frequency is not that high that you can actually think about using optical photons to drive that nuclear transition. And the half-life time, the coherence time of the system could be also comparable. This may be a little bit beyond the reach of the current laser technology in terms of the coherence time, but not that far out of the range. A few tens or hundreds of seconds, maybe thousands of seconds. You can always use power to saturate the transition to bring that down a bit. So we actually have been starting to work on this. I know there are many groups been working on this worldwide. We are a completely newcomer, and there have been a lot of research effort looking at what's the frequency of this thorium-229 isomer nuclear transition frequency is by looking at, for example, the decay to comparing the frequency difference between the two decay channels, one to the excited state, one to the ground state, and look at the energy difference, or a more recent approach that undertaken in Munich by looking at the excited decay to the ground state directly and look at the energy coming out of this decay process. And what we are working on right now is to try to build a laser system that we can directly drive the transition from ground to the excited, taking advantage of this very pioneering work that's been already reported in the literature by the Munich group. In particular, Lars van der Wens, who was one of the key members of the group in Munich that did this pioneering work of identifying where the transition is, the energyless landscape. He's now as a Humboldt Fellow in our group and is helping together with a graduate student, Changqun Zhang, to develop this VOV frequency comb that we have been working on for the past 15 years or so. Now we're getting to the point where each particular comb component will be able to tune over this nuclear transition with 100 nanowatt power per comb line. And we have actually done spectroscopy with these combs a few years ago using atomic transitions to sort of a test drive that. The line width is on the order of a kilohertz or so or below. We can actually stabilize the whole system to the strontium clock and silicon cavity. So this will be a fun project to look into to see whether we can truly using these vacuum ultraviolet photons around 150 nanometers with a very narrow line width, with a reasonably good power. They can estimate what's the Rabi frequency can drive this nuclear transition and see whether we can observe a direct transition frequency that's being predicted essentially, or placed a fairly tight bound of where the location of the transition frequency is by the Munich experiment. With that, I think I would conclude my talk. I want to thank many, many people contributing to these strontium optical lattice clock experiments, and really the quantum science and clock metrology combined in a number of different clock systems in our lab right now. And we have had long-running collaborations with many groups, but particularly worth noting is the collaboration with the PTB on the stable lasers, with NIST on the clock comparison, with Adam Kaufman on tweezers, and many theorists, Peter Zoller, Marina Saflanova, Paul Julian, Michel Lukin, and of course Anna Maria Ray, who's local in JILA, who have been key in developing some of the theoretical insight of the many-body physics. Thank you very much.